All right, guys, welcome to another episode of Cuda Education. This example is the ray tracing position fetch example that we're trying to investigate. Basically, what it is the GPU easily can give us barycentric coordinates, but in order to get the vertex data of a triangle, generally it would be a lot harder to do it. However, this example is supposed to make it very easy for us to get the coordinates of the vertex coordinates of the actual triangle. This is a very kind of math-heavy, abstract kind of thing, but I wanted to go over it just to give it its fair share of attention. From where I stand in my journey right now, I can't fully appreciate this feature, but I'm sure as we go along, it will come up again, and we won't be, it won't be brand new to us because we actually, we actually have this in our toolbox, and we did sort of made the effort to put this in our toolbox, so we're kind of familiar with it. But basically, when you run this application, you get this, but it's a very abstract and hard concept to really fully appreciate. See, we have a lot of triangles and stuff, and we have the shading on the triangles. But the best way for me to sort of, discuss this barycentric coordinates thing and us trying to get the position fetch. So when we say barycentric coordinates, we're talking about the weights that are associated with finding the point inside of the triangle. So let me step back for a second. Rays are generated, as we know, we have our ray gen shader. Rays are generated into our scene, and we eventually hit a triangle. Okay, so we generate rays into a scene, and we hit a triangle somewhere in the plane of the triangle. Now, what is easy for the GPU hit hardware to get, what is easy for the GPU hit hardware to give us is the weights associated with the point of intersection. So as you can see, as I move this around, we have weight 1, 2, and 3. The only rules we have with these weights, specifically for the weights, for each one of these numbers, for each one of the weights, the rule is that the weight has to be either greater than or equal to 0 or less than or equal to 1. Again, each individual weight, the rule is you're either greater than or equal to 0 or less than or equal to 1. So for example, if we have a hit point right on the A vertex, we have for the first weight a complete value of 1, and then for the other weights 0 and 0. Right? And every point in between, they're all either 0, 1, or positive, right? If we go to this vertex, vertex C, these two weights are 0 and this weight is 1. All right? And then if we go to vertex B, these weights are 0, this weight is 1. And every point within the triangle, we have positive values for the weights. Again, greater than or equal to 0, less than or equal to 1, right? Okay. If we're on the edge, we still get positive values, okay? If we're on the edge, we get positive values, right? These things are called, these weights are called barycentric coordinates. Now, when the GPU generates array and it hits something, it's easy for the GPU to give us these barycentric coordinates, these weights, because it is part of calculating the intersection. Don't want to get into the math, but basically the GPU needs these numbers because it needs to know whether an intersection occurred within this particular triangle. Okay? So remember I said each one of these values has to be greater than or equal to 0, less than or equal to 1, right? So that's the boundaries for each one of these values. There is also another constraint on these values. All right? The next constraint, and you might have guessed it already, is that all of these values have to add up to 1. Right? All of these values have to add up to 1. So if you add up all these values, you're going to get 1, right? So let us do some raw math. So 0.34 plus 0.35 plus 0.32 equals 1. This is because of rounding. Rounding error, guys. Rounding. Come on. Don't give me a hard time. All right. So 0.26 plus 0.21 plus 0.54. Right? They all have to add up to 1. And we saw this when we went to the vertices. Adds up to 1. Adds up to 1. Adds up to 1. Now, remember, these values are relative. They are relative to the vertex of the triangle. They are relative to the vertex of the triangle. Okay? So, and then if you notice, if you straddle the line, you know, one of them goes to 0, but then the other two picks up the slack, right? So this is what we call barycentric coordinates, okay? There are certain things you can do if you only have the barycentric coordinates, but there are other things that you can't do if you don't have the actual vertex values. Let me pause here. It's a very important discussion. What happens if you only have the barycentric values? If you only have the barycentric values, what it's saying is that, like, this is vertex A, B, and C. So A, B, and C, okay? So what it's saying is that if you only have the relative weights, the only information you have is your position relative to the vertices of the triangle, okay? The only information you have is your position relative to the vertices of the triangle. But you don't know specifically the locations of the vertices. I'll repeat. If you only have barycentric coordinates, if you only have the weights, you only have your position relative to the vertices of the triangle, but you don't know what the vertices of the triangle is. So for example, you know that you are 0.41 at this point D, right here. You notice that you're 0.41 away from vertex A. You are 0.34 away from vertex B, and you are 0.25 away from vertex C. If you go to vertex A, you are basically at A. And you're 0 and 0 weights as it relates to B and C. So notice that as we move away from A and we go to B, we notice that B increases and A decreases, right? So as we get closer to A increases and B decreases. As we get closer to B increases and A decreases, right? Notice that C notice that this guy remains relatively the same, okay? So barycentric coordinates only give you your relative position to the vertices of the triangle. It does not give you the coordinates of the vertices of the triangle. This is very important. You only know your relative position. All right, so I'm just trying to go through a couple of things. You only know your relative position as relates to the vertices of the triangle, but you don't know where the vertices are. It's like you're in a park. They drop you into a park, randomly drop you into a big forest or a big park. And I come to you and say, listen, this park is a triangle. And you are 0.32 away from vertex A, you're 0.45 away from vertex B, and you're 0.22 away from vertex C. You are a point in space, but you don't know where, you don't even know the shape or the contour of the park. You have no idea. You just know your relative position as it relates to the park, right? But you don't know the limits or the boundaries necessarily of the park. You just know your relative position. For an intersection test, this is important because, and the reason why it's important, remember I said each one of these values has to be greater than or equal to 0 or less than or equal to 1. All of the values combined has to add up to 1, okay? And this is our intersection test. Why is this our intersection test? It is our intersection test because if we have a point out here, we start breaking rules. We start breaking rules. First of all, one of the values is less than 0. That breaks a rule. Does it break the other rule? Okay, it doesn't break the other rule. But it breaks our rule that one of these values is negative. That breaks our rule. And in fact, all of these values break our rule. Right? Because there's a negative somewhere. Okay? This is barycentric coordinates. Fair use, guys. Fair use. I'm using this for educational purposes. Okay? So, notice that all of these values, it breaks our rule. Okay? So, by definition, the HID hardware already knows the barycentric coordinates, right? Because it has to do the intersection test. Notice as soon as we get back into our triangle, we are within our rules, which means there's an intersection, okay? That is barycentric coordinates, the relative weights as it relates to the vertices of the triangle. However, we need to get vertices of the triangle, and there's a million of reasons why you want to get the vertices of the triangle and all this stuff and attributes and special features and stuff. But for our purposes, just know that it's cheap to get the relative weights as it relates to the vertices of the triangle. But to get the actual coordinate data for the triangle is more computationally expensive, and you sort of have to do a bunch of stuff in order to get that vertex data. This is why in our example, Vulkan provided a feature. This extension is required for fetching position data in the closest hit shader. GLEXT ray tracing position fetch. So when it's saying position fetch and ray tracing basic position fetch, it is talking about getting the vertices of the triangle that you hit. All right, getting the vertices of the triangle that you hit. Now let's take it a step further. So that's what I'm going to discuss when we get back to code, okay? The Vulkan API gave us an easy way for us to pull the vertices of the triangle that we hit and get it into the shader. So remember, the shader stuff is like GPU related stuff, right? Remember, the source code is like on the CPU and stuff, but when we get into the shader stuff, we know we're fully running on the GPU, right? So we already have the barycentric coordinate stuff, but we need the coordinates of the triangle that we hit, okay? We need the coordinates of the triangle that we hit. And that's what this extension, ray tracing position fetch, is trying to give us. So let's pause for a second. All right, so we know that when we go out here, our relative weights, we know we're outside of the triangle just because this guy is negative, which breaks our rules. So we know that we're not hitting the triangle. This is wrong, you know, and we could do processing because we know that we're not hitting a triangle, right? And we have done this with a million times with the other ray tracing examples. You know, mesh shader, all that stuff. You know, we run the mesh shader here, and if we hit the triangle, we run the hit shader, and we have our ray gen shader and all that stuff. We've done that already. So here it's a miss, right? Now, let us watch magic before our eyes. Let us watch magic before our eyes. This stuff is greater than Harry Houdini, okay? Houdini. This stuff is greater than Harry Houdini. If you don't know who Harry Houdini is, ask somebody. So, we're breaking rules. We have two of these guys that are negative. I guess it's going to sum up to 1, but it's negative, okay? Now, watch what happens when I move this triangle from where it is now to where I have my ray pointing to. Watch when I move this triangle from where it is now to where I have my ray traversing. Uh-oh, what happens now? What happens now? What happens now? All of a sudden, we are within the rules. The relative weights are now within the rules. Why does this happen? And if I push this stuff over, we stay within the rules, right? If I push this stuff over, we stay within the rules. If I go up here, we're outside of the rules now, but if we go here, we're in the rules, right? Again, barycentric coordinates gives us the relative weights. So you don't really know the coordinates of the triangle that you're in the park. You don't really know the layout of the park or the contour of the park. You just know that you're either in the park based on your relative weights or you're not in the park. And you know your relative position to the vertices, but you don't know the actual vertices, right? You're not breaking the rules, you're breaking the rules, right? You're not breaking the rules, you're breaking the rules. And you could see the rules change, right? Just based on this. But we need to get the coordinates of the vertices, right? And again, there's a whole dissertation on why you need the vertex data, but I don't want to get into that right now. Now, again, if I move the ray, somewhere else, all of a sudden, that's outside of the triangle, I break the rule again. All right? So this is what well, okay, right. So we break, even when I go, now I'm not gonna start getting into like this breaks the rule, even though we're going past it, but I don't really want to get into what have you, right? But it breaks the rule because this is negative, right? And then as soon as I bring it back in, we're within the rules, right? I do want to see something. Okay. All right. So that's the problem I'm trying to solve. I will link this website below. There's a mathematical proof that I would also, so I will link this, and there's also another video that gives a mathematical proof as to why when these things add up to 1, and also non-negative and stuff, but like why these things always have to add up to 1, right? There's a mathematical proof, and it's actually pretty cool. So for you math heads out there, you will definitely appreciate it. I will link it in the comments in the description below. But yes, guys. So this is what we're trying to solve. We know our relative weights. That's easy for the GPU to give us, but then we want the coordinates of the vertices. So let's get back into the application, and I'll just start with the most direct and obvious thing. In the hit shader, we have to declare this extension. Extension GLEX ray tracing position fetch require. Okay, we need to declare this in our hit shader because down here, this hit triangle vertex position ext, these variables hold the vertices of our triangle, A, B, and C, right? And notice that we save it here. We save the vertex positions, right? That's the whole point of this extension here, is that it's easy for us to pull in the vertex positions into the shader and then do calculations and all that stuff, right? So we do calculation, we use it here, all that stuff, and we're doing calculations, right? But you could pull in the vertices, we could pull in the vertices of the triangle into the shader. That's what this is about. Now, that's what the hit shader is about. I don't believe, I think, so that's all this example. I'm not really sure how the running the application shows that, but it's a very nuanced and hard thing to really show in an application, right? But just know, this is an important thing. It's easy to get the relative positions, but then to get the actual vertices information, it's a little bit more tricky. The other stuff. So, okay, really quickly in our .cpp file, which is our source, the main source file. So this is our source file, and these are the shaders, right? Remember we talked about shaders being, directly on the GPU and stuff. The most important piece is that this guy here. Okay, so in the create bottom level acceleration structure function, create the bottom level acceleration structure containing the scene's actual geometry. So guys, we know that the bottom level acceleration structure is all about creating, declaring the vertices, declaring the mesh, the triangles, all the stuff that we're creating in our scene. Top level acceleration structure is doing multiple instances, one instance or multiple instances of these objects, but we actually have to declare the objects and the vertices and the mesh and all that stuff in the bottom level acceleration structure. So this guy right here, we have VK build acceleration structure allow data access KHR. We will access vertex positions from the bottom acceleration structure in the shader, right here. Right here. Okay, we will access vertex positions from the bottom level acceleration structure. So we need to set the VK build acceleration structure allow data access KHR. All right, so that's what this flag is right here for. It also shows up again down here. We will access the vertex position from the bottom acceleration structure. So we need to set the VK build allow data access. So it shows up right here. It shows up right here. And this right here is a hard boundary. If I comment out this thing, basically the application won't run. So I basically get a it wants me to do, it doesn't even show up. It wants me to abort and everything. Okay, so this is a hard boundary right here, right? And it's all under the create bottom level acceleration structure. So there's that guy, and then there are a couple other things that just to be complete, I have to mention. Down here, get enabled features, enable ray tracing position, struct physical device ray tracing position fetch features KHR, right? So it is also mentioned request ray tracing position fetch feature at device creation time. So right, we're creating the device and we need the position fetch feature for that. We also need to up here where is it? Okay. All right, I'll just go up here. Okay, so enable the sample specific extension. So enable device extension, ray tracing position fetch extension name. The corresponding GLSL extension is that. So this guy is this guy here, but in the sample enable device extensions, this guy. This enables shader can access GL hit triangle vertex position ext. So shader can access these guys right here, right? That's what this is for. All right. And then let's just go back to where we were previously. Tells driver that shader will fetch triangle positions directly from bottom level acceleration structure. So this bottom level acceleration structure is sort of, we're enabling it to basically transfer this information to our shader so that we have the vertex data and we could do various things with it, right? Normal calculation and all that stuff, okay? If you only have the relative positions, If you only have the relative positions, there are certain things you can't do. But if you have the complete picture, then you could do other things. There's some things like with wireframe and, you know, all of that stuff. You could generate a wireframe and stuff because you know where the vertex positions are and all this stuff. But I don't really want to get into that because it would just, you know, make things more complicated. And that's pretty much it, guys. I mean, it's really hard to sort of, all that I explained, it's really hard to get all of that from this, you know. I don't know if it's the different hues or something. I don't know. But I just wanted to break this one down for you guys, so, you know, we could complete all of the ray tracing examples. So let's see. We have done ray tracing basic. We have done ray intersection. We've now done ray tracing position fetch. We've done ray tracing reflections. We've done ray tracing shadows. So let's see the ones that we still need to do. We still need to do ray tracing textures, ray tracing shader binding table data, ray tracing GLTF. I think I did ray tracing callable already. I think I did that one already, but I'll do it again just for completeness and to finish the series. And then ray query is not necessarily ray tracing, but I'll see what that one is about. But anyway, guys, that is fair use. Fair use, guys. All of my material, it's fair use. It's for educational purposes. Fair use. I will link this website down below. Again, I say that there is another a couple of videos that basically, you know, especially I want you guys to watch the video about the proof for why this has to add up to 1. Why it has to add up to 1 as a constraint, and then I don't know if it necessarily goes to why it has, you know, they can't be negative, but yeah, remember all of these weights is like rays. So it's rays coming from here, rays coming from here, rays coming from here, and between the 3 weights you get your point, right? So yeah, watch the other video, especially the mathematical proof. I mean, I don't expect you to write it down or anything, but towards the end of the video, you will see the mathematical proof of why this always has to add up to 1. You know, inside of here. And that's it, guys. If you are interested in running these examples, you need to have a Windows computer with a Vulkan-capable GPU. If you want to run the ray tracing examples, you need to make sure your GPU is ray tracing capable. For NVIDIA, that's RTX and later and greater. I don't know about Intel and AMD. That's tutorial number 1, installs the Vulkan API on your machine. Tutorial number 13 installs all of these examples on your machine. Again, Windows-based machine, Vulkan-capable, ray tracing capable if you want to run the ray tracing examples, and especially this example. But again, it's hard to, and you could check out this thing too right here, but it's hard to it's hard to really communicate this in sort of a visual application. But with this guy, we could kind of work our way through it, right? But that is what the position fetch feature is about. It made it very easy for programmers to pass this information in. Otherwise, there's all kinds of complications, descriptor sets, descriptors, all kind of stuff, memory stuff. You probably have to deal with stride and all that stuff. This extension made it easy for people who needed the actual vertices of the triangle to be able to do so. So barycentric coordinates, guys, I never knew this stuff existed. I did not know the importance of this stuff. So as I learn, you guys learn. It's pretty cool stuff. I'm sure we'll see it again at some point. But remember, ray tracing is all about pushing rays into a scene and dealing with the intersections. So again, the GPU can easily give us the weights, the barycentric coordinates, but then if you want the actual vertex data of the triangles, it gets messy. So I will link some videos below. Please watch those videos also. Tell your friends about this. Thank you for watching. Have a great day.